Okay, in this lecture we're going to cover the first part of our section 2.5 material on equations of lines and planes in space. So in this lecture we're going to focus on equations of lines in space. And if we think about defining lines in the plane, so what we've been working with in Calculus 1 and 2, we know that the equation of a line in 2 dimensions can be defined by the slope of the line and a point on the line. So similarly, for a line in 3 dimensions, we need 2 things to define our line. So let's introduce the following concept. A line in 3-dimensional space can be determined by a point, x naught, y naught, z naught, which lies on that line, and a vector, which I'm going to denote as v, whose components are a, b, c, which is parallel to the line. So we have to have a point on our line, and the concept of a slope, but in 3 dimensions, would be that this line lies parallel to a vector which points in a given direction. And this vector v, which specifies the direction in which our line is moving or extending along, is called the direction vector for that line. So let's try to visualize this. In 3-dimensional space, let's say that we have our x-axis, the y-axis, and our z-axis. Maybe we're just looking in the first quadrant of space. And let's say that we have some point that lies on a line. This point we're going to call x naught, y naught, z naught. It's any point that lies on my line. And let's say that I have a vector v, whose components were given in as a, b, and c. And this vector is parallel to my line. So to visualize my line, well, I know what point it's passing through, this x naught, y naught, v naught, and I need to ensure that it's parallel to this vector v. So this is the line L that we're interested in. So let's think about how we could define equations for this line. So if we're interested in representing other points on this line, let's take any other point on this line. We'll call it x, y, z. Now we can see that the vector whose initial point is x naught, y naught, z naught, and whose terminal point is x, y, z, would be a vector that lies on this line. I'm going to call that vector A. So here, let me start by saying a vector on the line would be a vector A whose initial point is x naught, y naught, z naught, and the terminal point is some point x, y, z. So the components of this vector will be x minus x naught, y minus y naught, and z minus z naught. And we can see, well, since this vector A lies on the line and the vector v is parallel to the line, that means that the vectors A and v must be parallel. So here, I'll say since A and v are parallel, that means that A is a scalar multiple of v. Save myself a little room here, I'll write it as A is equal to some constant multiple of the vector v. So I'll call that constant multiple t. So writing that equation, well, A was the vector x minus x naught, y minus y naught, z minus z naught, and that has to equal t times v. So here, if v was the vector whose components are a, b, c, if we multiply that by the scalar t, we would have the vector a times t, b times t, and c times t. So in order for these two vectors to equal one another, their components must be the same. So equating the first components, we have x minus x naught is equal to at, y minus y naught is equal to bt, and z minus z naught is equal to ct. So if I solve this first equation for x, I would have x naught plus a times t. Solving the second equation for y, I have y is y naught plus b times t. And solving the third equation for z, we have z naught plus c times t. So these equations for x, y, and z can be used to define any point x, y, z on the line. So the idea here is these three equations are saying, well, we're starting at the point x naught, y naught, z naught, and then we are adding some scalar multiple of this vector a. So as this scalar t is ranging through all real numbers, we're looking at all different scalar multiples, including negative scalar multiples of the vector a. So we're extending along this entire line. So this set of three equations, which define points on the line, are called the parametric equations for the line passing through the point x naught, y naught, z naught, and parallel to a vector ABC. So these three equations were x is x naught plus at, y is y naught plus bt, and z is z naught plus ct. So one way that you might remember this is for the x, y, or z equations, you start with the coordinates for the point on your line, x naught, y naught, z naught, and then you add a scalar multiple, t times a, t times b, or t times c, of the components of this direction vector. And the value of t that we're using here is some real number, which is known as a parameter. Now, another way that we could express this set of equations for a line is as a single vector equation. So we would say the vector equation of this line is given by the vector r of t, whose first component is x naught plus at, the second component is y naught plus bt, and the third component is z naught plus ct. So if we take those three parametric equations for our line, that is for x, y, and z, and we put them into the x, y, and z components of a three-dimensional vector, we would say that that is a vector equation of that line. And finally, if a, b, and c are non-zero, so that is if the components of our direction vector are non-zero, then we would say the symmetric equations of this line are given by x minus x naught over a is equal to y minus y naught over b, which is equal to z minus z naught over c. And these equations come directly from the parametric equations for the line by solving for the parameter t. So for instance, if I look at my first parametric equation here, if I solve for t, I would have x minus x naught all over a. Similarly, if I solve the second parametric equation for t, I would have y minus y naught all over b. And if I solve my third parametric equation for t, I would have z minus z naught all over c. So we would say that our parameter t is equal to any of these three expressions, so they must all be equal to one another. In this form of the equations for the line are called the symmetric equations of that line. So for any, or in summary, for an equation or for a line in 3 dimensions, we have to have a point on the line and a vector called the direction vector, which is parallel to our line. And if we have those two pieces of information, we can find equations for our line, either in the form of parametric equations, a vector equation, or symmetric equations. So let's take a look at some examples working with equations of lines in 3 space. So in this first example, we are asked to find the vector equation and symmetric equations for the line passing through the point negative 2, 4, 5 and parallel to the vector v, which is 3, negative 1, 6. And then we are asked to find 2 other points on the line. So here, this point that we're given is our x naught, y naught, z naught. That is our point on the line. And the vector v that we're given here is our direction vector, which we were denoting in general as ABC. So here, if we want the vector equation for our line, we're looking at the vector r of t, whose first component would be x naught, which is negative 2, plus a, which was 3 times t. Our second component would be y naught, which is 4, plus b, which was negative 1 times t. And our third component would be z naught, which was 5, plus c, which is 6 times t. So this would be our vector equation. We're also asked to find symmetric equations for this line. So here our symmetric equations would be obtained by solving these parametric equations, which are the components of our vector equation for the parameter t. So if I solve this first equation for t, keeping in mind that this x equals this expression, I would have t is equal to x plus 2 over 3, which has to equal whatever we get when we solve the second equation for t. So if y is 4 minus t, then t would be 4 minus y over 1 here. And then that would equal to, if we are solving our third equation, which is z equals this expression for t, we would have z minus 5 all over 6. So here we found our vector equation for this line and our symmetric equations for that line. And in the last part of this problem, we're asked to find 2 other points on the line. So let's think about how we could find them. So to find points on our line, we could take our vector equation for the line and look at the components of that vector equation for different values of t. So in order to find points on our line, we might try choosing easy values of t to substitute into our vector equation. So for instance, if t was 0, we would have the point negative 2, 4, 5. which was the point that we were given on our line. So to find other points on the line, well, let's try choosing other easy values of t. So I might say something here to find points on the line. Let us choose values of t. So here we might use, if t is equal to 1, then we would have the components of our vector as 1, 3, 11. So that terminal point of that vector would be a point on our line. And we could take maybe t equals -1 as another point, or to get another point on our line. So if t is -1, we would have the components of our vector as -5, 5, -1. So these would be two other points that lie on our line. And to get more points which lie on this line, we could just take other values for t. And they don't necessarily have to be integer values. Here, t could be any real number. So let's look at some other examples. In this next problem, we are asked to find parametric equations and symmetric equations for the line passing through the points A and B, which are given there in the problem. And we ask, where does this line intersect the xy plane? So recall for a line in 3 dimensions, we need two things to define it. We need a point on the line, and here we're already given 2 points on our line. And we need a direction vector, that is a vector which is parallel to our line. So if we're considering a line from, or that's passing between 2 points, A and B, a direction vector would be any vector that lies along that line. So we could take the vector from point A to point B as our direction vector. So let me start by saying, let us take our direction vector v to be the vector from point A to point B, whose components would be 4, 1, and 6. So here, this is our direction vector for the line, and we have at least one point on our line. So here I'm going to use the first point A as my x0, y0, z0, and the components of this direction vector v will be what we're calling ABC. So for parametric equations of the line, we would have x is equal to x0, which was 1, plus a, which was 4 times t. Y would be equal to y0, which is -3, plus the second component of our direction vector, which was 1 times t. And then z would be equal to z0, which was 2, plus the third component of our direction vector, which was 6 times t. Now you could also use point B as your x0, y0, z0. So another valid choice here might be 5 plus 4t, -2 plus t, and 8 plus 6t. That set of parametric equations would define the exact same line. Now we're also asked for the symmetric equations for our line. So let's say here, those were our parametric equations, and our symmetric equations are obtained by solving each of these for t. So solving my first parametric equation for t, I would have x minus 1 over 4 is equal to, solving my second equation for t, I would have y plus 3, which is equal to, solving our third equation for t, we'd have z minus 2 over 6. So first off, our parametric equations, and then our symmetric equations for that line. Now we're also asked to determine where does this line intersect the xy plane. So let's think about how the xy plane is defined in space. Now for any point on the xy plane, we know that the z coordinate must be 0. So we're asking where the line, whose parametric equations are shown here, would have a z coordinate of 0. So let me say to find where this line crosses the xy plane, which is the plane where z equals 0. We're going to take the parametric equation for z, which was 2 plus 6t, and set it equal to 0. So we find that 6t is negative 2, and t would be negative 2 over 6, or negative 1/3. And so x would be given by 1 plus 4 times t. So here I'm looking back at my parametric equation for x. Once I know what t is, I can substitute back into the equations for x and y to find the x and y coordinates for that point of intersection. So my x value would be 1 plus 4 times negative 1/3. Or 1 minus 4/3, which would be a negative 1/3. My y coordinate would be negative 3 minus 1/3. So altogether negative 10/3. And then z is 0. So here for our final answer, the point where this line crosses the xy plane would be the point negative 1/3, negative 10/3, and 0. Okay. Now in our next example, we are asked to show that the line passing through the points A and B, whose coordinates are given, is perpendicular to the line through the points C and D, whose points are given. So let's think about how we could show that two lines in space are perpendicular to one another. So a little illustration here. Let's say that we have two lines, we'll call them L1 and L2, which are perpendicular. So how could we, or what does it mean for these two lines in space to be perpendicular? Well, the direction of each of these lines, L1 and L2, is specified by some vector. So let's say we have a direction vector for our first line of V1. And we have a direction vector for our second line of V2. So if these lines are perpendicular to one another, that means that their direction vectors must be perpendicular or orthogonal. Now, the only way that two vectors are orthogonal is if their dot product, V1 dot V2, is equal to 0. So if we can find the direction vectors for these two lines and show that their dot product is 0, then we've shown that these two lines are perpendicular. So let's start with the direction vector for the first line through the points A and B. So here, a direction vector for the line through point A and point B would be the vector from point A to point B. So the components of this vector would be 1, -2, and 5. And a direction vector for the line through points C and D would be the vector from point C to point D, whose components would be 3, 4, and 1. So if we take the dot product of AB with CD, let's see what we have. So the product of the first components of those two vectors would be 3. Product of the second two components would be -8, and the product of the last two components is 5, which leaves us with 0. So that means that AB and CD, these two direction vectors, are orthogonal, which recall was just sort of a vector terminology for perpendicular vectors. So since these direction vectors are orthogonal, the lines are perpendicular. So this is one way that we can show that two lines in space are perpendicular to one another, is that their direction vectors are orthogonal. Similarly, if we wanted to show that two lines in 3 dimensions are parallel, we would need to show that their direction vectors are parallel. So that is the direction vector of one line is a scalar multiple of the direction vector for the other line. Now, the next thing we'll talk about in this section is how to determine the distance from a point in space to a line. This is a problem of interest that will come up somewhat often throughout our course and might have some nice physical applications. So let's go about stating our theorem here. This theorem gives us a formula for the distance from a point to a line. So here, let us take L to be the line through the point P, which has a direction vector V. So if Q is any point which does not lie on the line L, then the distance from the point Q to the line L is given by D for distance, and it's the ratio of the magnitude of the cross product of the vector PQ with the direction vector V divided by the magnitude of that direction vector V. And here I claim that we can get a pretty simple proof for this, so let's consider our problem of interest. So let's sketch what we're looking at here. We have in 3 dimensions some line L, which is passing through some point P. So P was a point on the line. And then we said, well, let's take any point Q which does not lie on the line. And what we're interested in finding is what is this distance from the point Q to the line L. And when we say distance from a point to a line, we're referring to the shortest distance from that point to the line. So the direct path from the point to the line so that these intersect at a 90-degree angle. So the idea here is this length of this little segment is what we're calling d for distance. And in order to find this, well, we're going to take a vector from point P to point Q. So here we can see that we're forming a right triangle. And let me take theta to be the angle between my line and this vector PQ. And here our line has direction vector v. So we could say here, somewhere along our line, we have this direction vector v. So what I'm trying to derive is this formula for the distance from the point to the line. So let me start by considering the value for sine of theta. So here, sine of theta, where theta is the angle between our direction vector and this vector PQ. In terms of our triangle, so let's say we have a little right triangle being formed here. So sine of an angle, in terms of the sides of a triangle, is defined as the ratio of the opposite side, or the length of the opposite side, which would be d, to the hypotenuse, which would be the length of this vector from point P to point Q. So solving for d, we would have the magnitude of this vector from P to Q times sine of theta. However, let us recall from the previous section, section 2.4, we had a theorem for the magnitude of the cross product of two vectors. So here, if I'm looking at the magnitude of the cross product of PQ with the vector v, one of my theorems from section 2.4 said this is equal to the product of the magnitudes of these vectors, p, q, and v, times sine of the angle between them. So if I solve this equation for sine of theta, I have sine of theta is equal to the magnitude of the vector PQ cross V divided by the product of the magnitude of PQ and V itself. So substituting that expression for sine theta into this equation that we had above for distance, we find that the distance from our point Q to the line L is given by the magnitude of PQ times sine of theta, which we just found as the magnitude of PQ cross V, divided by the magnitude of PQ times the magnitude of V. So here, since Q is not a point on the line, we know that the magnitude of PQ is non-zero, so I can cancel this factor of the magnitude of PQ in the numerator and denominator. And I'm left with the magnitude of PQ cross V over the magnitude of V. And this was the formula that we had given in our theorem. So we've now given our derivation for that formula. So now that we have this formula for the distance from a point to a line, let's look at an example of this. So we're asked here to find the distance between the point Q, which was 0, 1, 3, and the line with parametric equations x, y, and z given there. So there's a couple of things I need to apply this formula. First, I need a point that lies on the line. I need a point P, which is on my line. So to find a point on the line, let's choose some value of t to substitute into these parametric equations. Let's take maybe t equals 0. So for our point P, which lies on the line, if t is 0, x would be 1, y would be 1, and z would be 5. So here P, which is this 0.115, is a point on our line. So once I have that, I need to find a vector from point P to point Q. So here, the vector from point P to point Q would have components of, let's see, -1, 0, and -2. And I also need to find v, which would be a direction vector for my line. So recall, in general, the notation we were using for that direction vector was the vector whose components are little a, little b, and little c. And we can read those components of the direction vector directly from our parametric equations. We had x is x naught plus a times t, y is y naught plus b times t, and z is z naught plus c times t. So the coefficients in front of t for our parametric equations are going to be the components of our direction vector. In this case, -1, 2, and 3. Now, once we have these vectors for that distance formula, we need to find their cross product. So here, looking at the cross product of PQ with the vector v, we're taking the determinant of the 3 by 3 matrix whose first row consists of our standard basis vectors I, j, and k, whose second row consists of PQ, which had entries -1, 0, -2. And our third row is the vector v, which was -1, 2, 3. So for the I component of this cross product, we would take 0 times 3 minus -2 times 2. So that gives us our I component is 4. For the j component, we would take the product of -2 and -1 and subtract the product of -1 and 3. So here we would have 2 minus a -3 is 5. And then for our k component, we would take the product of -1 and 2 minus 0 times -1, which gives us -2. Now the numerator of our distance formula is the magnitude of this cross product. So let's look at the magnitude of this vector PQ cross V, which would be the square root of the sum of the squares of their components. So that is the square root of 16 plus 25 plus 4, which leaves us with the square root of 45, or 45 is 9 times 5, so square root of 9 is 3 times square root of 5. And we also need the magnitude of the vector v for the denominator of our distance formula. So looking at the magnitude of the direction vector v, we would have the square root of 1 plus 4 plus 9, or root 14. So finally, once we have these components, we can substitute them directly into our distance formula, and we would have 3 times the square root of 5 over the square root of 14 as the distance from our point Q to the line whose parametric equations were given. Okay. Now the next thing we'll start talking about in this section is the concept of skew lines. So we know if we're working in 2 dimensions or in the plane, any 2 lines in the plane are either equal to one another, that is, they're the exact same line, they are parallel to one another, but they are not equal, or they intersect in a single point. However, in 3 dimensions, there is a 4th case which is possible. So we can have either 2 lines are equal to one another, so they lie directly on top of one another. They are parallel but not equal, so they pass through different points but have the same direction vector. They intersect at a single point, or in 3 dimensions, if we have 2 lines which are not parallel but also do not intersect, then they are called skew lines. So 2 lines which are not parallel to one another, but which also do not intersect are called skew lines. And in the figure below, I've given a little image to illustrate an example for skew lines. So here we might have some line L2, which is parallel to the z-axis, and then a line L1, which has some direction vector. And we see that L2 lies sort of behind L1. So these 2 lines would never intersect in 3 dimensions. So that's what we would call skew lines. So let's consider an example of skew lines. So here in our next problem, we are asked to determine whether the lines with parametric equations given below are parallel, intersecting, or skew. So we have 2 lines, L1 and L2, and the parametric equations are given. For the line L1, we're using a parameter t, and for the line L2, we're using a parameter s. And then we're told if these 2 lines do happen to intersect, we want to find their point of intersection. So let's think about how we would do this. So in order to determine whether these 2 lines are parallel, we would need to look at their direction vectors. So let's consider the direction vectors for these 2 lines. So here the direction vectors for L1 and L2 are the vectors, I'll call them V1 and V2. So for the line L1, the components are the coefficients of t in our parametric equations are 2, 1, and 4. So that would be our direction vector for the line L1. And for the line L2, the coefficients of the parameter s are 1, 2, and 3. So we can see here that these 2 direction vectors are not parallel. Here, in order for these vectors to be parallel, one would have to be a scalar multiple of the other. So comparing their first components, if I went from 1 to 2, I would have to multiply the vector v2 by a scalar 2. But I see if I take the second component and multiply by 2, I do not get the second component of v1. So I'll say here, since v1 and v2 are not parallel, that means that the lines L1 and L2 are not parallel. So we've ruled out the case that they are parallel. So they are either intersecting or skew. So to determine if they are intersecting or skew, we would compare the parametric equations for x, y, and z for these two lines. So let me start by saying if the lines intersect at a point, let's call our point x, y, z, then the x, y, and z equations would have to be equal to one another for line 1 and line 2. So in order for these two lines to intersect, they would have to have the same x coordinate. So we would have 1 plus 2t is equal to s, or maybe, let me just save myself a little space, write it like this, 1 plus 2t is s. The y coordinates would have to be the same, so t would have to equal to 2s minus 2, and the z coordinates would have to be the same, so 1 plus 4t would have to equal 3s minus 2. So I have a system of equations involving three variables. So if I simplify this a little bit, I could try to solve this. So let's take a look at what we have here. Our first equation gives us s in terms of t. So in order to try to solve for t, let's take that expression for s and substitute into my later equations. So here, taking my first equation and substituting it into the second and third equations, I would have the following. T, so let me give some description here for the purposes of the notes. Substituting s, which is 1 plus 2t, into the second equation, gives us the following. T is equal to 2 times s, which was 1 plus 2t, minus 2. So simplifying a little bit here, we have t is equal to 2 plus 4t minus 2, so the plus 2 minus 2 cancel. And then moving all of my t's to one side, I would have 3t is 0, and so t would have to be 0. Now if t is 0, then s, which is 1 plus 2 times t, would be 1. So we now have, if t is 0 and s is 1, we've satisfied our first two equations, but we need to make sure that the third equation is also satisfied. So let's say the following. If s is equal to 1 and t is equal to 0, then the third equation is given by, well, we had 1 plus 4 times t, which was 0, would have to be equal to 3 times s, which was 1 minus 2. So we would have 1 is equal to 1. So if s is equal to 1 and t is equal to 0, then all three of my equations are satisfied. So that means that there is some point of intersection for these two lines. So let me give myself a little room here. So we can say the lines intersect, and we're supposed to find their point of intersection, x, y, z. So in order to find it, we could either take t equals 0 and substitute into the equation for our first line, or we could take s equals 1 and substitute into the equation of our second line. So here, either approach we use will get the same point. So I'm going to take t equals 0 for my first line, and I would get the point 1, 0, 1. So here, these two lines intersect, and the point of intersection is the point 1, 0, 1. So let's look at another example, which is somewhat similar. Here we are supposed to show that the lines with parametric equations given below are skew lines. And here, let's see, so if we're told they're skew, they're non-intersecting, we can omit this second part of the problem. So here, to show that these lines are skew lines, we have to show that they are not parallel and they also do not intersect. So as with our last example, to show that they are not parallel, let's compare their direction vectors. So I'll say the direction vectors for these two lines are, for the first line, L1, our direction vector would be 1, 3, negative 2. Those are the coefficients of the parameter t in the first line. And V2, which would be 2, 1, 1. Those are the coefficients of s in the parametric equations for the second line. So let's determine if these are parallel. Comparing the first components, if I went from 1 to 2, I would have to multiply V1 by 2 to get the first component of V2. But comparing the second components, if I multiplied 3 by 2, I would not get the second component of V2, which is 1. So since these direction vectors, V1 and V2, are not parallel, the two lines, L1 and L2, are not parallel. They are not parallel, so all that we need to show to see that they are skew is that they are also not intersecting. So as with our last example, we could say the two lines intersect at a point if the x coordinates for these two lines would be equal to one another. So that is if t minus 3 is equal to 2s minus 1. If the y coordinates are the same, so if 3t plus 8 is equal to s minus 1, and if the z coordinates are the same, 5 minus 2t is equal to s minus 4. So we want to see if this system of three equations has a solution. So I'll mention here solving our first equation for t. We would have t is equal to 2s plus 2. So if I take that first equation and add 3 to both sides, we get the following. So if I take this and substitute into the second equation, let's see what we have. So on the left-hand side, I add 3 times t, which is 2s plus 2, plus 8. has to equal s minus 1. So simplifying, we would have 6s plus 6 plus 8 is plus 14, has to equal s minus 1. So moving all of our s's to the left-hand side, I would have 5s has to equal, moving all of our constants to the right-hand side, I'd have negative 15. So s is negative 3. And if s is negative 3, then substituting into our equation for t, well, I would have 2 times s plus 2. So that would be negative 6 plus 2, or negative 4. So now we know that if s is negative 3 and t is negative 4, we've satisfied the first two equations of our system, but we need to check whether this third equation is true for those values. Let me say then, substituting into our the third equation, let's see what we have. So the left-hand side would be 5 minus 2 times t, which was negative 4, would have to equal s, which was negative 3 minus 4. So on the left-hand side, we would have 5 plus 8, or 13, would have to equal negative 7, which is not true. We have a contradiction. So that means that there is no value, or there are no values of s and t that would satisfy all three equations at the same time. So that means there is no point of intersection. So here we could say the lines do not intersect. So we've shown that they are not parallel and they do not intersect. And so we can say they are, therefore, skew lines. So this is what we wanted to show for that problem, that these two lines are skew, which by definition means that they are not intersecting and they are not parallel to one another.